Okay, so now let's take a look at the multiplication and division rule. And we're going to see the same thing happen in addition and subtraction, the same thing that happened in that the rule is the same for both of those calculations. So addition or subtraction doesn't make a difference. The rule is the same. And the same will occur for multiplication and division. Now, we'll use the same kind of process that we used for the addition and subtraction video, and that is that we will look at the range. We will figure out in a mathematical calculation involving multiplication and also division, what is the largest possible answer we can produce in taking into consideration the uncertainties, and what is the smallest possible calculation we can make. So to make this a little bit more real world, I'm going to give you a velocity of 18.5 plus or minus 0.6, and that's in meters per second, and a time of 5.2 seconds plus or minus 0.5 excuse me, seconds. Now the equation is d is equal to v times t. I'm so sorry. So all we're going to do is multiply these two numbers together. So I'll follow the same range method that we used before. I'll figure out the answer to the calculation. I will figure out my high number, my low number, the range of those two values, and then the uncertainty will be determined from that. Okay, so first things first, very easy. Let's just multiply the two numbers together. 5.2 times 18.5. As you can see, I already did it there. That is equal to 96.2, and that would be in meters, right? So this is a calculation. Velocity times time will give me a distance or a displacement. All right, so now what I need to think about is how do I produce the biggest calculation possible? Well, I hope it's pretty obvious at this point that if I add this uncertainty, I'll end up with 19.1, and if I add this uncertainty, I'll end up with 5.7. And those are the biggest possible values for these two measurements, so therefore those are going to give us the largest possible value. So 19.1 times 5.7, and that is equal to, I know my calculator just acted very weird, but 108.87. The low number would be achieved by going with in the opposite direction. So we'll go 18.5 minus 0.6 would be 17.9 times, and then we're going to subtract the 0.5 from this one, which would give me 4.7. So that is 84.13. All right, so what we want to do now is to get the range. So I'm just going to subtract those two numbers. That was 108.87 minus 84.13 to give me a range of 24.74. So that's about 25. And then we'll divide that by 2, and that gives me 12.37. Okay, what I would suggest that you would do is use the regular rules for rounding. Realize we can only keep an uncertainty up to 2 digits at a max. Now, since this is going up to the tens, I'll go ahead and keep these 2 digits, but I'm going to drop these guys off. Now, of course, I'm going to look to see if this is going to tell me to round up or not. So is this number closer to 13 or is it closer to 12? In this case, it's closer to 12. Not a lot closer, but a little bit closer. So my uncertainty and my final answer for this calculation becomes 96 plus or minus 12. And then that would be in meters. Okay, so what I would like to do now is let's do the division, and you will see that something is a little different from what we had before. So what I'm going to do for the division problem is I'm going to make this the change in the velocity. So that way we can do change in velocity divided by the time. That would be the acceleration. So for our division problem, and I'm purposely putting this very close to the previous one because I'll show you the rule down here at the bottom. But look, this isn't that complicated. The multiplication division rule, I think using the range method, that is kind of a smart way to do things because it's relatively simple calculations. It's logical, it makes sense, but where it runs into problems is when you do the division, because the division rule is a little bit more complex. You have to think about it a little bit more. How do you produce your biggest value and your smallest value with that calculation? So let's say, for example, that delta V is equal to 18.5 plus or minus 0.6, and that our time is equal to 5.2 plus or minus 0.5. That's meters per second and seconds. And now we're going to do an acceleration calculation, which says delta V over delta T. All right, so same process. A HLRU. So first thing we'll do is the division. That's going to be 18.5 divided by 5.2. That is 3 point. I'm going to write all the numbers out to several places past the original number, and then I'll decide later how many of those need to get cut down. So that is 3.55769. Okay, so the division is done. Now we need to think about, how do I produce my biggest number? Now this is where you really have to think about things very clearly. The biggest number in division problem, when you're doing division, the biggest number will be when the number on top is the biggest and the number on the bottom is the smallest. We want to divide by the smallest possible value we can get on the bottom. So this is a little different. Instead of adding to both of them to produce my biggest answer, I'm going to add to the top one, but I'm going to subtract from the bottom one the uncertainty in order to get the biggest possible answer. So that would be 19.1 divided by 4.7, and that's 4.06. Okay, the low number would be doing the exact opposite. So I'll subtract the 0.6 from the top number, I'll add the 0.5 to the bottom number. So in that case, that is going to be 17.9 divided by 5.7, and that's 3.14. Okay, so the range we would simply subtract 4.06 minus 3.14. Oops. That is 0.92. I will say divide that by 2 to give me 0.46. Okay, so you have two options with this. You could do a single digit, and in that case, oh, I'm so sorry. In that case, if you do a single digit for your uncertainty, then you would have 0.5, right? Because this says that we're going to keep the first digit. That means it's going to be in the tenths position. I look at the next number to decide, is this number closer to 5 or closer to 4? It's closer to 5 because we're above half here. So I can give you two possible answers for this one. That answer would be that it is 3. Oh my gosh. I can't believe I said 3 and wrote 4. 3.56 plus or minus 0.46. And remember, this does have units. That is in meters per second squared. Or I could give a single digit answer, which would be equally valid, and that answer would be 3.6, because remember, it's 3.55. So if I'm going to cut it off here, then that means I look to the next digit to decide whether I'm going to round up. It is a 5, so I will round up. It's 3.6 plus or minus 0.5. Again, in meters per second squared, and either answer would be acceptable. If you go more than that for the number of sig figs on the uncertainty, then you're definitely going to be deducted. Now, obviously, just take a look. Notice that the answers did not come out anywhere near each other. I did not get the uncertainty. So this one was 12 and this one was 0.46, and they're not even in the same units, right? This is meters per second and that's meters. That's a big difference with addition and subtraction. You can only add numbers or subtract numbers if they have the same units. So there's no problem with the units. So not only is there a problem with the number, but then these units wouldn't even work out anyways. It doesn't even make sense. You can't compare these two at all. So the rule is a little bit more complicated. And so now let's establish what is the rule. I'm going to simply write the rule, and then we'll go through and we'll practice, and we'll recreate these two by following the rules. And you'll see that the rule is the same for both calculations, but it produces a different answer. So the rule is that if you have a calculation that Q is equal to either A divided by B or A times B, then the way that you would find the uncertainty is through this formula. It says delta Q, remember, delta Q is the result of the calculation. It's what we got when we divided or when we multiplied. Delta Q over Q. Hopefully you recognize this as the fractional uncertainty. So I've taken the absolute uncertainty and divided it by the answer.